Hello students, let us now talk about expected value and standard deviation, or probability standard deviation. What is an expected value? Here's the definition. We just multiply the payoff times the probability and add them all up. You can consider the probability as the weighing of appropriate outcome, and adding them all up, you get sort of an average. If you don't like the sigma notation for the sum, then you can use this kind of expression as well. Just add, dot, 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 all the way to the end. Let's see, do we have an example here? Let's go to this example. Simple example, and let's keep it simple. 5 red, 3 green, 2 blue balls. And we have this random variable, and let's calculate the expected value for the random variable capital X. Okay, what's the payoff value? That's 0. And what's the probability? Red? 5 red. So 5 out of 10. And that's red. Next, what's the next payoff? Green. And what's the probability? 3 green balls. And that's green. Now blue. Payoff is $3 and the probability is 0.2 because there are 2 blue balls there. And then calculating all these, red, blue, red, green, blue. Let's run it. 1.2. And that's the expected value. It's easy computation. Now, does it make sense? Well, the smallest possible value is 0. The largest possible value is 3. We got somewhere in between, so it does make sense. And in terms of gambling model, this is basically the payoff that you expect each time you play this game. Now, if you play this game, say 1,000 times, or even better, 10,000, 100,000 times, and then average out, that's going to be more or less equivalent to getting the expected value. And the more repetition you have about this game, then the better approximation, the better estimation the expected value will be. And exactly how better, and then how much error to expect, that's something we're going to discuss in Chapter 8, Module 8, Module 9, I think, when we deal with central limit theorem. But at this moment, consider this as a probability mean. How about the next game? Well, do we have enough time for the next game? Well, okay. I mean, it's just a simple computation, so negative 1.5 times the probability of red, 0.5, 50 cents, and the probability of green, plus $1 times the probability of blue, and what do you get? R G B, and this computation yields, if I remember correctly, something negative. Okay, negative 0.4. So if you play the first game, then you are expecting to win $1.20 each time you play the game. And then if you play the second game, you're expected to lose about 40 cents each time. And if you repeat it for something like, I don't know, 100,000 times, then it averages out about losing about this much each time. And for example, in the first game, what if the price to play this game is $1.50? In that case, you're going to be losing 30 cents, right? Approximately speaking. And if you put the price to play this game as subtract 1.5 here, subtract 1.5 here, subtract 1.5 here, and then run the computation, in the end you're going to get negative 30. Excuse me. let's okay, I'll do a little bit different games, so let me put a little bit different symbol here. So 1.50, excuse me, that's the price to play this game. So you pay $1.50 to play this game, and then we have all these payoffs and probability, and then if you run, then you're gonna get, well, as expected, negative 0.30. So from here, subtract 1.5 and then getting this, or subtracting in advance to all the payoffs. Either way, you're going to get the same thing. So whether you start from here and then subtract away the price to play the game, or get those included in each of those payoffs, either way, you're going to get the same thing. Does it make sense? Anyway, that's the expected value for you. Okay, so much for expected value, and let's go to variance and standard deviation. Again, those are just formula computations, so they are not going to be too bad. And here's the variance. Each outcome, or each payoff, minus the expected value, and square those. Now, if you don't square, if you simply take x minus mu and then multiply the probability and add them all up, you're going to get 0 because this difference, as a matter of fact, this thing is called deviation. Each deviation, xi minus mu, have positive or negative, and they're going to cancel each other out. You're going to get 0. But if you take square and then make all the deviations into deviation square, which is positive, in that case, if you add them up, you're going to get positive value. That's called the variance. Now, once you get the variance, take the square root, and that's called the standard deviation, or probability standard deviation. It is a little bit related to the previous standard deviations that we studied earlier, the population standard deviation and sample standard deviation. And the computation is kind of similar too. We have deviation squared added up, but here we have what? Frequency over the population size. We need those kind of things. And if it's what I just said doesn't make any sense to you, never mind. I'm not going to do any proofs, so let's just move on. In any case, you can consider these as just computational formulae, and you should know how to calculate these. Now, if you don't like the sigma notation for the sum, you can rewrite these like just adding them up, add with dot, 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 either this way or that way. Just fine. But, the sigma, whenever you mean sigma, Greek letter sigma, the capital sigma, excuse me, that means summing them up. So it's useful to remember this. Now, how about some exercises? Oh, before going over to exercises, the standard deviation measures the dispersion. So the smaller the standard deviation, the more concentration. The bigger the standard deviation, more dispersion. Let's go to these problems here. How about the standard deviation? Okay, here's a good problem. So let's calculate standard deviation of the first game X. Well, we have to calculate the variance first. All right. And here we need deviation squared, output minus expected value, and we have to square it. Minus expected value square minus expected value square, and if you calculate all this, you're going to get the variance. $1.56. Okay, looks like that's a variance. Now, standard deviation. That's the variance, square root of the variance. So therefore that is square root of 1.56. Oops. And okay, I have it. So the first game has this standard deviation. So this measures the diversion, the dispersion. How about the second game? Well, okay, we have, yeah, I don't need this. How about the second game? Okay, this is the expected value computation. And let's do the variance computation. From here, I have to subtract away the expected value, right? And then I have to square that. But then again, minus minus, nobody calculates this way. Changes to plus. Here, subtract negative 40, so plus 0.40. And then plus 0.40. And then let's calculate this thing. What do you get? $1.24. That's the variance. Okay, let's calculate the standard deviation. No, sigma of y, excuse me, I have a typo here, and that's square root of the variance, and that is approximately equal to square root of 1.24, and that is approximately equal to, let's calculate square root of 1.24. Okay, this is what I got. Okay, that's the probability standard deviation of the second game. So let's go to the first game and the second game. And comparatively speaking, the first game has a little bit bigger standard deviation, so it's a little bit more dispersed out. And then the second game has a little bit smaller standard deviation, so it has a little bit more concentration. How about this game? You see, from game X, I just inserted the price to play the game, negative 1.5. And then it turned out that it doesn't matter whether I subtract 1.5 first to each payoff here and do the expected value computation, or subtract it later. Now, what do you think will happen to standard deviation? The answer is, well, I'll leave the answer to you, the computation to you, and the answer will turn out to be the same as before. Use your common sense. Is there any kind of dispersion, further dispersion, simply by inserting the price to play the game? No rule change, just price change. So it may affect the expected value, but not the dispersion. Not convinced? Do your computation. I'll leave you here.